In the previous few lectures, we have discussed the Dirac equation, and just in the previous lecture, you have seen the different important properties of Dirac matrices. Or in other words, you can say you have learned about the Dirac algebra. Now, what you have learned in the previous lectures regarding the properties of Dirac matrices, I would like to illustrate those facts, those concepts by some important illustrative examples. So in fact, regarding the illustration of Dirac matrices, I will take two classes, or you can say I will provide two videos. So this is the first video on the illustration of Dirac matrices. And after these two lectures on illustration, you will have a complete knowledge of Dirac matrices. And then you can even solve some unseen problems based on these Dirac matrices in your examination. Okay. In fact, in this first lecture, I am going to deal with only one example. But in the second lecture, we will see two or three examples which will be very important for your examination. Okay, so let us see what is our first example here. I have taken the first example like this, that if alpha represents the three Dirac matrices, that is alpha x, alpha y and alpha z. You also denote these Dirac matrices by alpha 1, alpha 2, alpha 3. Okay, and B and C are usual three-dimensional vectors. Okay, these are vectors B and C. In fact, in that condition, we have to show that alpha dot B times alpha dot C is equal to B dot C plus I sigma dash dot B cross C. In fact, here this sigma dashed is actually a 4 by 4 matrix, and it is defined by like this. This is just sigma 0 0 sigma matrix. Here sigma you know it is the well known 2 by 2 polyspin matrices. Okay, you have a complete idea of polyspin matrices. I have provided videos on this polyspin matrices previously in very detail. Okay, and you have also learned the matrices alpha and beta in terms of this poly matrices. Okay, so let us see how we can solve this problem. This is a very simple problem by following the different properties of Dirac matrices which you have learned in the previous lecture. If all those properties are in your mind, you can solve this problem very easily. Okay, so let us see. Actually, in this problem, we have to prove that this alpha dot B times alpha dot C is equal to B dot C plus I sigma dashed B cross C. Okay, so first of all, let us see how we can express these vectors and these matrices in the terms of their scalar components. Let us see. You can write this alpha equal to alpha xi plus alpha yj and alpha zk. This is just a usual manner to write down the vector or matrix. Okay, in 3 dimensions. And this vector B, which is an ordinary geometrical vector, that can be represented as bxi plus byj and bzk. And similarly, the vector C is represented by cxi plus cyj plus czk. In fact, this bx, cx, by, cy, bz, cz, these are x, y and z components of the vectors B and C. Okay. Now, we will find separately what will be alpha dot B. You can see alpha dot B, it means you have to take the scalar product of these two quantities. And you know from the definition of a scalar product, A dot B is AX BX plus AY BY plus AZ BZ. So alpha dot B, that will be simply equal to alpha X BX plus alpha Y BY plus alpha Z BZ. And similarly, this alpha dot C, you can see this will be alpha X CX plus alpha Y CY plus alpha Z CZ. So let us start with the LHS. and arrive at the RHS. Okay, so in LHS there is alpha dot B times alpha dot C, but we have seen that alpha dot B is equal to this much and alpha dot C is equal to this much. So let us substitute these two values at the place of alpha dot B and alpha dot C. So I have written here that this is equal to alpha x bx plus alpha y by plus alpha z bz times alpha x cx plus alpha y cy plus alpha z cz. Now let us take the multiplication. You can see when we will take the product of alpha x bx with alpha x cx, what will be this? This will be alpha x square bx cx. Okay. Now take the product of alpha y by with alpha y cy. Okay. So this will be alpha y square by cy. Now take the product of this alpha z bz with alpha z cz. Okay. This will be alpha z square bz cz. Okay. Now we will take the product, the remaining product. In fact, we will take the product of this alpha x bx with alpha y cy, and that will be alpha x alpha y bx cy. Now multiply alpha x bx with alpha z cz. So this will be alpha x alpha z times bx cz. Okay. Now we will take the product of this alpha y by with the remaining terms, and that will be what? Alpha y by times alpha x cx. So this will be equal to alpha y alpha x times by cx. Okay. Now multiply this alpha y by with alpha z cz. So this will be alpha y alpha z by cz. Okay. Now we will take the product of remaining terms with this alpha z bz. You can see when you will take its product with alpha x cx, this will be alpha z alpha x times bz cx, and the product of alpha z bz and this alpha y cy will be what? This will be alpha z alpha y times bz cy. Okay. Now you have learnt in the previous lecture when we have studied the properties of Dirac matrices that the square of all these Dirac matrices, that is alpha x square, alpha y square and alpha z square, all these are equal to 1. Okay. And at the same time we have also learned that these matrices alpha x, alpha y and alpha z do not commute, but they anti-commute. Okay. They anti-commute. And so what you have learnt in the previous lecture, let us apply it here. You have seen in the earlier lecture that the anti-commutator of alpha x alpha y, this is equal to 0. Okay. And it means this is anti-commutator. Okay. And this is alpha x plus alpha y alpha x equal to 0. And so alpha x alpha y is equal to minus alpha y alpha x. Already you have learnt this fact in your previous lecture. And I have written here, you can see the square of these matrices is equal to 1, which we have learnt in the previous lecture. Now similarly you can say that this alpha z alpha x is equal to minus alpha x alpha z, because any pair of these three matrices anti-commute. Okay. And alpha y alpha z is equal to minus alpha z alpha y. Okay. Now we will use these results in the previous equation which we have actually seen here. This is the result. In this result, at the place of alpha x square, alpha y square and alpha z square, we will put 1. Okay. So the first three terms will be simply bx cx plus by cy plus bz cz. Now let us see. Here there is alpha x alpha y. I am marking it by dot. And you can see in this term which is marked by this dot, there is alpha y alpha x, but you have seen that this alpha y alpha x is equal to minus alpha x alpha y. So this will be taken as a common factor, and then the remaining term will be bx cy minus by cx. Are you getting the things or not? This is very simple calculation. You can easily understand. So you can see I have taken this alpha x alpha y as a common factor, and the remaining terms will be then bx cy minus by cx, applying this property. Okay. Similarly, you can see the remaining terms. Here there is alpha x alpha z, and here there is alpha z alpha x. Okay. I am marking it by this cross symbol. So you can see this alpha z alpha x is equal to minus alpha x alpha z. So again here alpha z alpha x will be common, and the remaining term will be bz cx minus bx cz. Okay. And similarly, this alpha y alpha z, I am marking it by 3 cross here. This is actually equal to minus alpha z alpha y. Okay. So this alpha y alpha z will be also common. So doing all these algebras, you can write this result in this manner, that this alpha dot b times alpha dot c is equal to bx cx plus by cy plus bz cz, because all these square of matrices is equal to 1, and alpha x alpha y times bx cy minus by cx plus alpha y alpha z times by cz minus bz cy, and alpha z alpha x times bz cx minus bx cz. Okay. So we simplify this LHS alpha dot b times alpha dot c equal to this much. Okay. Now this bx cx plus by cy bz cz, this will be simply equal to b dot c from the definition of a scalar product. You can see, and we will also evaluate what actually these bracketed terms represent. For this, let us find the scalar and the vector product of O. But before that, let us see here. First of all, our aim is to find this alpha x, alpha y, alpha z, and alpha z, alpha x. First of all, we will find it, and then we will find this scalar product and the vector product of B and C. So you can see here alpha x alpha y. As you can see in our problem, it is given that the 4 by 4 matrix, this sigma prime is equal to this matrix. Okay, sigma 0 0 sigma, where sigma is the polyspin matrices. So if you will write any component of this sigma prime, let us say we have to write sigma x prime, then here at the place of sigma we will write sigma x, here also we will write sigma x. And if you want to find the sigma y prime, then at the place of this sigma we will write sigma y, and here also we will write sigma y. Similarly, when you will find sigma z prime, then in this matrix sigma will be replaced by sigma z. Okay, this is a very simple concept. So let us see what will be this alpha x alpha y. Now according to the given condition in our problem, that this alpha x will be in fact here alpha x and alpha y is given. You have learnt in the previous lecture in the property of Dirac matrices that this alpha matrix is defined in terms of the polyspin matrices, and this was defined like this: 0 sigma and sigma 0. Can you remember? The alpha was defined like this. So here I have defined this alpha components of alpha, And if you want to define the component of alpha, which you have learnt in the previous lecture, then you can write at the place of this alpha, we will write this 0 sigma x 0, and this alpha y will be 0 sigma y 0 matrices. Okay, this is just is very simple two matrices, and you have to find the product of these two. You can see we will take the product. What we will do, 0 times 0, that will be 0. Okay, plus sigma x times sigma y, sigma x times sigma y, sigma x times sigma y. So the first term will be first element will be simply sigma x sigma y. Okay, now we will take 0 times sigma y, that will be 0, plus sigma x times 0, that will be 0. So the second element is 0. Okay, this is a simple product. You can understand. You have definitely a knowledge of finding product of matrices. Now sigma x times 0, this will be 0, and 0 times sigma y, that is also 0. So this is equal to 0, and so this element is 0. Okay, now sigma x times sigma y, so this is sigma x sigma y, and plus sigma y, 0 times 0, 0. So this is sigma x sigma y, so this element is this much. Okay, now you have also learnt in the while studying the polyspin matrices, when I have provided videos on polyspin matrices, and you can see that video, and definitely you have an idea because you have definitely watched those videos too. Then where we study the polyspin matrices, there you find the different properties of polyspin matrices, and one of the very important property of polyspin matrices is what? It is I sigma z is equal to sigma x sigma y. Okay, I sigma x, this is equal to sigma y sigma z. I sigma y, this is equal to sigma x sigma z, sigma z sigma x. Okay, so from the property of polyspin matrices, we can replace this sigma x sigma y by I sigma z. Okay, so here I have also replaced the sigma x sigma y by I sigma z, and you know this can be written as I times sigma z 0 0 sigma z. Okay, but in our problem it is given that this sigma dashed matrix is equal to what? This is given that this is sigma 0 0 sigma. It is given in our problem. You can see what I was talking about previously. This is here. You can see this sigma prime is equal to this much. So if you now want to find any component of this sigma dashed, you have to put the corresponding component inside this matrix. So from the given condition, we can easily write here that this sigma z 0 0 sigma z, this matrix is will be simply equal to sigma dashed z. Okay, so I have written here, you can see that this sigma x sigma y is equal to I sigma z dashed. Okay, I sigma z dashed. And in the similar manner, when you see by induction, you can write the other results as the products of sigma x sigma y is I sigma z dashed. So on this basis, you can see when there is subscript x and y, then in the result there is z. So similarly, you can say that this So sigma x sigma 1, but I have written it here wrongly. In fact, this will be not sigma but alpha x alpha y. See here, it has been written wrongly. This is alpha x alpha y. So alpha x alpha y, this is equal to what? This is equal to I sigma z dashed. Okay, I sigma z dashed. Okay, so in the similar manner you can write alpha y alpha z equal to I sigma x dashed, and sigma z alpha z alpha x equal to I sigma y dashed. Okay, now after getting the values of these products alpha x alpha y alpha z alpha x, which actually occurs in our this equation 1, alpha x alpha y alpha z alpha x. Now we will see what the other terms represents. Bx cx plus by cy plus bz cz, this is simply b dot c. This will be simply b dot c. So you can see that will be b dot c, and here I have mentioned that bx cx plus by cy plus bz cz, this is equal to b dot c. Okay, now I have used those results here, and so this alpha dot b times alpha dot c is equal to bx cx plus by cy plus bz cz, and instead of alpha x alpha y I have written here I sigma z dashed this much, and instead of alpha y alpha z I have written here I sigma x dashed, and instead of alpha z alpha x I have written I sigma y dashed. Okay, so this sum bx cx plus by cy plus bz cz is equal to b dot c, but now we will see what these remaining, the sum of these remaining terms actually represent. For this, let us find the value of the S vector product of these two vectors b cross c. You know, b cross c is defined in this determinant form. This will be a 3 by 3 determinant, and from the definition of vector product you can write it ijk bx by bz cx cy cz. Now solve this determinant. When you will take this I, okay, then there will be a product of by cz minus bz cy. So this is by cz minus bz cy. Okay, in second term, in determinant in the formula there is minus, but I have written here plus, so operation will be just reverse. Okay, so when you will write plus, then the term will be bz times cx minus bx times cz j. Okay, and when you will take this k as common factor, then this will be bx cy minus by cx. So you can see that actually this first term, which is the coefficient of I, that is by cz minus bz cy, this is the x component of the vector b cross c. Similarly, bz cx minus bx cz, this is the y component of vector b cross c, and bx cy minus by cx, this is the z component of the vector b cross c. The page has been turned, but this will be okay, don't be worried. So let us see. Okay, so I have found the vector product of this much. So you can see when we will now find the scalar product of the vector sigma dashed, which is defined like this: sigma dashed equal to sigma x dashed I plus sigma y dashed j plus sigma z dashed k. Then the scalar product of this sigma dashed and b cross c vector will be what? In the scalar product, we simply take the product of the corresponding components and added them. Okay, so this will be equal to sigma x dashed times cz minus bzcy, because x component of b cross c vector you have seen, this is equal to this much bycz minus bzcy. Okay. Similarly, the second term will be what? This will be sigma y prime times bzcx minus bxcz, and the third term will be sigma z dash times bxcy minus bycx. This is very simple calculation. Okay. So when you will use these results, that is instead of the expression in RHS of equation 3, we can write sigma dash dot b cross c. Okay. And at the place of this sum bxcx plus bycy plus bzcz, we can write b dot c. So substituting all these values in this equation number 2, what you will see, what you will get. Instead of this, we will write b dot c, and you can see in all the remaining 3 terms, this I is a common factor. So take this I as a common factor, then the remaining term will be simply equal to sigma dashed dot b cross c. Okay. And this is the result which we have to prove. You can see. So you can see how easily we can solve this type of problem if all the properties of Dirac matrices are in your mind. You have seen that during the solution of this problem, we have used several times the different properties of Dirac matrices. We have also used the properties of the polyspin matrices, which you have learned sometimes earlier. If you have not studied the polyspin matrices in detail, I will suggest you go through my video in this same playlist on the polyspin matrices. You will find a detailed discussion on the polyspin matrices in those videos. Okay. And as I have told you, this was only one illustrative example, but in the next lecture we will see some more important examples on this Dirac matrices, and that will be very helpful to you, and in your examination such type of problems is invariably asked. So after watching all the videos on illustrative example, you will have a concrete knowledge of Dirac matrices. Okay. Thank you very much.